Have you ever stopped to think about the invisible forces that are shaping our worlds? And I'm not talking about gravity, I mean something born right in the heart of the atom itself. Today, we're going to dive deep into the absolutely fascinating and powerful world of radioactivity. So check this out. On one side, you've got this incredible machine, a gamma camera. It's a total lifesaver that lets doctors peek inside our bodies to find diseases. And on the other side, well, you've got this. It's a universal symbol for danger, warning us about a powerful, invisible threat. So, what gives? That's really the big question for us today. How can the exact same force be a tool for incredible healing and also a source of immense danger? Well, the answer, it turns out, happens on a scale so tiny, it's kind of hard to even wrap your head around. To really get this, we've got to go right to the source of it all. We're going inside the atom. You know, the basic building block of literally everything. Okay, so quick flashback to science class. You probably remember this. Every atom has this tiny, dense center called the nucleus. And inside that, you've got your positive protons and your neutral neutrons. Then you've got these tiny negative electrons just zipping around the outside. Simple enough, right? Now here's the thing to remember. The number of protons is like an atom's fingerprint. It tells you exactly what element you're looking at. Carbon always has 6 protons, period. But the number of neutrons? That's where the plot thickens. And that leads us to a really important question. What happens when you have atoms of the same element, so they have the same number of protons, but they're carrying a different number of neutrons? And here is the perfect example. Just look at carbon. All 3 of these are carbon atoms, no question, because they all have 6 protons. But look closer. Carbon-12 has 6 neutrons, carbon-13 has 7, and carbon-14 has 8. They're like different versions of the same thing. And there's a special name for these different versions. Isotopes. You've got to remember this word. It's key. Same element, same protons, just a different number of neutrons. And that little difference, well, it changes everything. So, here's the twist. Not all of these isotopes are stable. Some of them, like that carbon-14 we just saw, have a mix of protons and neutrons that just doesn't work. The nucleus is unbalanced. It's got way too much energy, kind of like a spring that's been wound up way too tight. So what's an unstable nucleus going to do with all that extra energy? It's got to get rid of it somehow to calm down. And it does that through a process called nuclear decay. This is radioactivity. The nucleus just spontaneously kicks out energy or particles. And that, my friends, is the radiation we're here to talk about. So, when one of these unstable atoms decides to let go of some energy, it doesn't just do it in one way. It's got a few options. You can think of them as different flavors of radiation. The 3 main types are alpha, beta, and gamma. I absolutely love this way of thinking about it. Imagine an obstacle course. The alpha particle is like the big, bulky strongman. It's powerful, but it gets stopped by the very first wall. The beta particle is a little quicker, a little more nimble, it gets a bit further, but the gamma ray, whoosh, it's like a ghost. It zips right through almost everything. It's a perfect mental image for their penetrating power. Okay, let's get into the nitty-gritty here. So an alpha particle is basically the core of a helium atom. It's a heavyweight. A beta particle is just a super fast electron. And gamma rays, well, they aren't even particles. They're just pure, high-energy waves. As you can see, these 3 are totally different from each other, and that has some huge consequences. And this brings us to a super important trade-off. The alpha particle, the big bowling ball, has the highest ionizing effect. That means it's really good at smashing into other atoms and causing damage. But because it does that so well, it loses its energy fast and is easy to stop. A piece of paper will do it. Gamma rays are the complete opposite. They have a low ionizing effect, but they have insane penetrating power. They can go right through you. Okay, so we know these unstable atoms decay, but the decay of any single atom is totally random. You can't predict it. So how on earth do we measure it? Well, we use a concept that acts like a surprisingly predictable radioactive clock. And we call that clock a half-life. It's simply the amount of time it takes for exactly half of the radioactive atoms in a sample to decay and turn into something else. It's not the time for everything to disappear, just half of it. This graph makes it crystal clear. Let's say you start with 120 million atoms of iodine-131. You just watch and wait. After 8 days, poof, you're down to 60 million. Half of them are gone. That's the half-life, 8 days. And if you wait another 8 days, bam, it halves again,
down to 30 million. It's this incredibly predictable pattern.
All right, let's tie this all together. We now understand unstable isotopes, the three types of radiation, and the idea of half-life. With all that in our toolbox, we can finally go back and tackle our original question. How can this force both heal us and harm us? Let's start with the healing. Doctors can inject a patient with a special substance that has a short half-life and gives off gamma rays. Now, why gamma? Remember, it's the one that can pass right through things, so it can get out of the body for the camera to see. And why a short half-life? Well, you want it to do its job and then disappear quickly to minimize any harm. It's a medical tracer. So cool. Here's a piece of tech you probably have in your house right now, a smoke detector. It uses a tiny bit of a substance that emits alpha particles. Remember how alpha particles are great at ionizing things? Well, they ionize the air inside the detector, creating a tiny electrical current. But if smoke gets in, it breaks that current and beep, 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 the alarm goes off. It's actually brilliant. And what about isotopes with a crazy long half-life? Take uranium-238. Its half-life is 4.5 billion years. So by measuring how much uranium has decayed into lead inside an ancient rock, geologists can figure out exactly how old that rock is. It's like a clock for the entire planet. I mean, these applications are just incredible. But there's a flip side. The very properties that make radiation so useful, especially that ability to ionize atoms, are the exact same properties that make it so dangerous. See, when that ionizing radiation passes through our bodies, it can be like a tiny wrecking ball, smashing into our cells and, most importantly, our DNA. That can kill cells, or even worse, it can cause them to mutate, which can lead to cancer. And as we saw with uranium, things with a long half-life stay dangerous for thousands, or even billions of years. And that brings us full circle, right back to where we started, with this duality. Radioactivity gives us things like nuclear power, which is totally clean energy. But it also creates nuclear waste that's deadly for millennia. It gives us medical tools that save lives, but those tools have their own risks. So the final question really isn't just for physicists. It's for all of us. How do we, as a society, balance the incredible progress this invisible force enables with the very real peril it poses?